All right, I got I got a calculator. I don't have mine, but we can get this started now. Determine whether Rolle's theorem. We didn't do this one, did we? I was gonna do it, and then yeah, okay. So I did like some of it, but then I didn't have my calculator, so I stopped. So Rolle's theorem is like it's a corollary of the mean value theorem, but there's just one thing that has to happen, is that the endpoints here, when you plug them in, they have to equal the same value so that there's basically a level playing field. And so instead of setting your derivative equal to a to the average rate of change, you're setting it equal to 0, but it only works if this is 0. So let's make sure. Okay, first of all, this is a polynomial, so he's continuous. There's no indifferentiable everywhere. So we're going to go ahead and plug in an f of 4. We're going to plug in an f of 0. Okay, and f of 4, f of 0. Let's do this quick. Okay, f of 4, 3, 4 squared minus 12, 4 plus 11 equals 11. And so we're just going to copy this guy and put in a 0. Oh, yeah, well, I can see 0 times 0, minus 0 plus 11. So it both equal 11, okay? So therefore, this n f of x is differentiable and continuous. Okay, I'm just going to put that. So right now, everything can be applied. So what we want to do now is, since those guys line up, what we're going to do is we're going to find out where this guy's derivative equals 0. So let's go ahead. Well, I wrote derivative. Shoot, I didn't want to rewrite this whole thing again. But I'm going to take the derivative of this guy. He ends up with 6x minus 12. Set that equal to 0. Put 12 on the other side. And then we get an x equals 2. Okay. So this means that c equaling 2 is the location where the derivative is going to be 0. He's going to be, in a sense, the average rate of change between 2 points that are level is going to be 0. So that's all. So really, it's just a hyperextension of the MVT. Okay. Now right here, looks like this is good too, unless you throw in a 0. Let's throw in a 0 here because we got to get this guy. It's going to be negative 7. And then g of 7 equals 2 times 7 squared minus 7. And that definitely is not going to equal negative 7. All right. So wait, why did I throw in a 7? Throw in a 3. It doesn't make any sense. Okay, wait. So just to be safe now, I got 18 minus 7. Okay, it still doesn't equal negative 7. Okay, so therefore, Rolle's theorem does not apply. Rolle's does not apply. Okay, and you want to say it doesn't apply because g of b, that is g of 3, does not equal g of a. Okay, so b is the second guy, a is the first. Okay, they don't equal each other, so therefore they won't apply. All right. A cylindrical can holds 1 liter of cubic centimeters, 1,000 cubic centimeters of liquid. How should the height and radius be chosen to minimize the amount of material to manufacture the can? All right, we've done something like this before. Okay, let's get that can, draw a picture. Okay, and we know that the volume is going to be, it's going to be the area of the bottom circle and then multiplied by the height. So pi r squared times height is going to give you the the volume of this guy. But you want to minimize the amount of material. So what you're trying to do is you are trying to, let's see, you are trying to limit the amount of the surface area. Okay, so cylindrical can holds that much. How much will be chosen? Okay, so we need the holds 1 liter. Okay, so we know the volume equals 1,000. Let's just go into centimeters. Okay, so let's do 1,000, and that's going to be this guy. Let's divide by that right there. Okay, we've done this before. I know what's coming. We did the surface area, and so we had to like substitute h for something that involved r. Okay, we can only do one variable. So now when we go to the surface area, okay, the surface area is 2 of those circles, okay, it's area, plus the circumference of that circle times the height, okay? Not pi r squared, that would be the area, okay? We just want that basically the label of the can, okay? Okay, so surface area equals this guy. We're going to go ahead and switch out that h right here so that it's 1,000 divided by pi r squared. The pi's cancel out, and so does one of the r's, okay? So now our new one is going to be 2 pi r squared plus 2,000. And we're going to go ahead and put that r to the top, but we're going to make them a negative exponent, okay? And that's because I'm going to be taking its derivative in just a second. So I'm going to set this guy equal to 0, okay? And I'm going to take the derivative at the same time, okay? I probably shouldn't do that, but I feel like I'm running out of space. So 4 pi r minus 2,000 r to the negative 2. So now we're going to move this guy over to the other side. Okay, and I'm going to rewrite this guy again, and you will notice that I can cross multiply. So then the r goes to the other side. We get 2,000 equals 4 pi r to the third power. Once we cross multiply, we're going to divide both sides by 4. And why do I not trust myself? What is that? 500. 500 equals 4. Nope, I divided by 4 already. Okay. So now we've got r to the third power equals 5,000 divided by pi. And then we're going to take the cube root. Okay. So let's go ahead and notice that this is the radius. Okay. So the radius right there. Let's just... we can actually, that's where it's going to get minimized here. Let's just go ahead and figure out what that number is, okay? What is the cubed root, which is, the cube root is actually in math. You got to go down to 4. Cube root of 5,000 divided by pi. Okay, it's 11.7. Okay. All right, so that's going to be 11.7 centimeters. So if we want the height, okay, then we're going to have to do 1,000 divided by pi times that same guy, 11.7. Well, here, let's actually, times... push up, grab that guy, close it up, equals, there we go, 27.3. Okay, so the height has to be 27.3 centimeters. Okay, now I wonder if we multiplied those guys, we better actually get a volume of 1,000. So I just want to double check. Okay, so pi times r, which was this guy, and we're going to square that guy, times h, which was this guy, should give us 1,000, but it doesn't. So what's up? I feel like something's wrong. Did I do something wrong? Ah, shoot. 11. Oh, I didn't square this guy. Okay, so I'm right. I just didn't square this guy. Let's raise him to the second power. Okay, enter. Okay, the height being that makes a little bit more sense. Okay, so now the height is 2.3. Okay, now that's interesting. So is that right here? Let's do pi times 11.7 squared times the height, which is 2.3, and there's 989. Now the reason why it's 989 is probably because of all of the decimals that I just trimmed away. Okay, so it's close enough, all right, for me to accept those to the tenths, okay? All right. So, next. Oh, why is this a max, or why is this a min rather than a max? Well, you'd have to take the second derivative here. And what you'd notice is that if you took the second derivative here, you would get 4 pi plus 2,000 r to the negative third. Nope, 4,000 r to the negative third, okay? And what you can do is you can plug in a number that is less than 11, okay, which we'll say 0. And if you notice that if you plug in a 0 for r, you will get a positive number. If it's positive, it's concave up, and therefore that's a min. Okay? So just take that second derivative, plug in your critical value, and see if it's just positive or negative, and then I'll tell you if it's concave up or concave down. Okay? Now that's a justification. That's only if they ask for a justification. Okay, next one. Where are we at time? 11 minutes. Poster is to have, let's see, I'm going to have to move this guy. Okay. Poster is going to have, okay, we did another problem like this before. 1-inch margins at the bottom and the top, and 2-inch margins on the sides. That's 2, that's 2, that's 1, that's 1. Okay. What are the dimensions that will give the largest printed area? The poster is supposed to have an area of 180. Okay, so this guy's an X value for the width, and this guy's a Y value. Okay, so the poster is supposed to be the area equals X times Y, and that has to equal 180. Okay, so the printed area is the whole area, okay? So let's go ahead and, we're going to solve for Y here. So 180 divided by X equals Y. And what we need to do is get the area of the entire thing, and that would be also length times width. And if you notice here, the length is X, but then you've got an extra 2 and an extra 2. So it's not minus like it was before, it's actually X plus 4. And then the length is actually Y, this piece, plus that extra 1 and that extra 1. Okay, so that's 2. So now what we've got to do is we have to substitute this right here for the Y. So let's go ahead and do that. And then we're going to FOIL. We're going to do it very carefully. Okay, so A equals X times this guy is actually just going to be 180 because the X's actually cancel out. But then we're going to get 2X, okay, when we distribute the X to the 2. And then we're going to get 4 times 180, which is 720. 720 over X, and that's going to be 8. Let's combine like terms. We get 2X plus 720. Let's make that guy X to the negative 1 because I know I'm going to be taking the derivative. Plus 188. Now let's take that derivative. We get 2 minus 720, and he'll drop a degree. And what we got to do, my printer made some noise. Okay, we're going to set that equal to 0. Let me rewrite this more cleanly. And I even missed the X there. Okay, there we go. That's the guy. We're going to move that guy over to the other side. 720 X to the second power equals 2. So now we're going to cross multiply. Okay, 2X squared. Divide that by 2. That's 360. 360 equals X squared. So X is going to be plus or minus the square root of 360. And you can leave it like that, honestly. Just leave it like that. All we need now is to figure out which one. Is it negative or is it positive? Well, I mean, if it was negative, we know that there's no way that that's possible. In fact, what is the square root of 360? Square root of 360 is 18 point, it's almost 19, okay? So let's go ahead and think about what makes sense here? Do we want the negative? No. If we want the negative x, that would make no sense. Okay. Okay. And we could actually take the square root of 36. 36 times 10, so that'd be 6 radical 10. So that looks a little better to me, so I'll just keep it like that. Now that is actually the x value. So now we're going to go ahead and plug it into here to get the y value. So 18 divided by 6 radical 10 is y. That goes in there 30 times. So now we got 30 over radical 10. And if you remember, we're not allowed to have radicals, so let's get that guy up here. Okay, so multiply both the top and the bottom by radical 10. These guys here. Now look, if you got the decimal for that, it doesn't matter. Like, that's just as fine. But I'm just kind of showing you that you've got this, it's the same thing. 30 divided by radical 10 is the same as 3 times radical 10. That's just, oh wait, 3, yeah, that's right. 3 radical 10, okay? All right, now those are the dimensions. You got 6 radical 10 plus 4 by 3 radical 10 plus 2. Okay, and if you turn that into decimals, great. That's totally fine. Feel free to do that. If you turn it into decimals, make sure that this equals the decimal that you got. Okay, so that's it. That's the only kind of optimization problem that you guys are going to experience. Okay, and we'll save this for the last video.